Okay, so in this video, what we're going to discuss is we're going to discuss finding the slopes of tangent lines to these polar curves. Okay, so in the last set of videos, we've talked about what the polar coordinates are. We've talked about finding some simple polar curves, and now we're going to start doing calculus on those polar curves. Okay, so in order to so the slope of our tangent line is always going to be dy dx. Okay, so this is always the slope of the tangent line. Okay, even though we're working in polar coordinates, the slope of our tangent line is always dy dx. Okay, and the way we're going to find dy dx is, in fact, we're going to treat this like a parametric equation. Okay, so what do I mean by that? I mean, remember we said x was r cosine theta and y is r sine theta. Okay, but if we think about our equation in polar form is r equals some function of theta, well, that means x is a function of theta and y is also a function of theta. This is really just a parametric equation where our parameter is theta. Okay, so that means dy dx is going to be dy d theta divided by dx d theta. Okay, dy d theta is going to be the derivative, so r theta sine theta, take its derivative, divided by the derivative of r theta cosine theta. Well, we have a product of functions in theta, so we can just apply the product rule. So this is r theta cosine theta plus r prime sine theta divided by r sine. Actually write this as prime theta sine theta cosine theta. There we go. Minus r sine theta. Okay, so I wrote the first one a little wonky. Usually write the term with the r prime first, but essentially how do I go from here to here? I'm just using the product rule that you learned way back in Calculus 1. Okay, so let's use this in an example. Okay, so for the curve r equals 1 plus sine theta. Okay, so remember we drew this in a previous video. This is the cardioid. It's going to look something like this. Part A, we are going to find the slope of the tangent line at theta equals pi over 3. Okay, so here's how we're going to do that. We need to find our, so the slope of our tangent line is just dy dx. Okay, so dy dx, remember is, I'll write it the typical way this way, r prime sine theta plus r cosine theta divided by r prime cosine theta minus r sine theta. Okay, we tend to simplify and know that r is a function of theta, so we don't usually write it as r theta or r of theta or r prime theta. Typically write it like this. Okay, so r prime is just the derivative of r with respect to theta, so in our case that's going to be cosine theta. So this is going to be cosine theta sine theta plus 1 plus sine theta cosine theta, all divided by cosine squared theta minus sine squared theta. Okay, and we can simplify this a little bit. But if we're just plugging in theta equals pi over 3 here for part A, we'll do some simplifications in the next step. So we're going to take dy dx, and we're going to plug in theta equals pi over 3. Okay, so this should be cosine pi over 3 times sine pi over 3 plus 1 plus sine pi over 3 cosine pi over 3, all divided by cosine squared pi over 3 minus sine squared pi over 3. Okay, and we can plug in, we know cosine pi over 3 should be a half, and sine pi over 3 should be root 3 over 2. So this should be 1/2 times root 3 over 2 plus 1 plus root 3 over 2 times a half divided by 1/4 minus 3/4. And I believe we can simplify this a little bit. So this first one should be root 3 over 4 plus, we can write this as 1/2 plus root 3 over 4 divided by negative 1/2. So that is 2 root 3 over 4, which is root 3 over 2, plus 1/2 divided by negative 1/2. So that should be, everything's divided by half, so that should be negative 1 minus root 3. Should be our slope. Okay, and if we go back to our graph, what this is saying is, what can we take out of this geometrically? We can say that our slope is negative. Okay, so at theta equals pi over 3, our slope should be negative. So theta equals pi over 3 should be, let's do this in this color, should be about here. And sure enough, we should have a negative slope. Okay, so at least that passes that smell test. Okay, so in part B, let's do what we always do with these types of problems and find horizontal and vertical tangent lines. Okay, and we usually restrict ourselves to be on 0 to 2 pi because, I mean, these curves infinitely repeat. Okay, so let's go back to our derivative. We wrote our derivative like this. So dy dx should be I just made a huge mistake. So this was r cosine theta, r sine theta. R was 1 plus sine theta sine theta. There we go. So that means this is going to be 1 plus sine pi over 3 times sine pi over 3. So this should be 1 plus root 3 over 2 times root 3 over 2. So it's not going to be quite as nice as it was before. So this should be, what, root 3 over 2 plus 3/4. So this should be negative 1/2 minus root 3 over 2. So oh, that's even better. Okay, because you have 1 minus root 3 over 2 in the denominator and 1 plus root 3 over 2. So this should just be negative 1. Okay. Again, the comment about negative slope still occurs. Okay, so this should be cosine theta sine theta plus 1 plus sine theta cosine theta divided by cosine squared theta minus 1 plus sine theta sine theta. Okay, so there's our derivative. This doesn't look like such a friendly form to do anything with, but notice everything in the numerator is multiplied by cosine theta, so we can factor out one of those. So we can factor out a cosine theta and a 1 plus 2 sine theta, and then in the numerator. And we can use the Pythagorean identity in the denominator and rewrite the cosine squared theta as 1 minus sine squared theta. So this is 1 minus sine squared theta, distribute the sine theta, minus sine theta minus sine squared theta. So this is going to be cosine theta 1 plus 2 sine theta all over, write it as negative 2 sine squared theta minus sine theta plus 1. And the denominator factors as well, which is going to be helpful for finding zeros. Okay, the denominator factors into 1 minus 2 sine theta and 1 plus sine theta. Okay, so let's focus now on the horizontal tangent lines. We'll have horizontal tangent lines when the numerator is 0. So 0 equals cosine theta times 1 plus 2 sine theta. Okay, so a product of things equaling 0 means that either cosine theta is 0 or 1 plus 2 sine theta is 0. Okay, so if cosine theta equals 0, that means theta is going to be pi over 2 or 3 pi over 2. And if 1 plus 2 sine theta is 0, then that means sine theta equals negative 1/2. And that happens when theta is going to be 7 pi over 6 and 11 pi over 6. Okay, we'll go back and look at our graph after we find the vertical tangents as well. You're going to have vertical tangent lines when the numerator is 0 or denominator is 0. So that's when 1 minus 2 sine theta times 1 plus sine theta is 0. Okay, so again, either the first term of the product is 0 or the second term of the product is 0. If 1 minus 2 sine theta is 0, then that means sine theta is equal to 1/2. And that means theta is going to be equal to pi over 6 and 5 pi over 6. Alternatively, we have 1 plus sine theta equaling 0 means sine theta is negative 1, which then means theta equals 3 pi over 2. Okay, so something I want to draw your attention to is notice theta equals 3 pi over 2 is on both lists. Since theta equals 3 pi over 2 is on both lists, it is in fact neither. Okay, so it's neither a horizontal tangent line nor a vertical tangent line. And let's go back and look at our graph to see why. Okay, so here's our graph. Okay, so we said that there should be 3 horizontal tangent lines. Okay, and sure enough, there's one at pi over 2, 7 pi over 6, and 11 pi over 6. We also have vertical tangent lines at pi over 6, which should be right about there, and 5 pi over 6, which should be right about there. Okay, so what's going on at 3 pi over 2? 3 pi over 2 is this point right here. So in terms of what we have of our graph is theta equals 3 pi over 2 is what's called a cusp. The derivative does not exist. Okay, so it's neither a vertical nor a horizontal tangent line. Thank you all for watching, and hopefully you spotted my mistake before I did. Thank you.